Okay, so now we heard from three manufacturers, and now we can have a representation from the production equipment stream. Now we have a presentation from Dr. Liang from Ideal Energy, who will speak about the industrial production ready PECVD equipment for high efficiency HJT solar cells. Liang is Vice President at Ideal Energy Sunflower Thin Film Equipment Limited, so not to confuse with the ALD arm of Ideal Energy. He has about 15 years of experience in semiconductor and PV equipment industry, serving as an R&D director at Comet Technologies US is one of his earlier jobs. So Liang, welcome, and please take the virtual conference platform.
Hello everyone, let me share my screen first. Wow. You see the slide?
Yes.
Okay, hello everyone. So my topic today is industrial production ready PECVD equipment for high efficiency microcrystalline HJT solar cells. I would like to share some of the considerations we have while we were designing our microcrystalline HJT tool. So first of all, a little bit commercial introduction to our company. So IE Sunflower is our company name. We have been developing PECVD tools for HJT for 9 years. And now we have our PVD tool as well, also for HJT. So we have 12 customers so far, and 9 of them has passed acceptance for our tool. The others, we're still working on it. We still need a little bit of time to ramp up. So those customers include like LONGi, Zhongwei, Huasheng, Risheng, Hanneng, etc. So one thing I would like to mention is our customer use our microcrystalline PECVD tool to set and hold HJT efficiency world record of 26.3. That was announced like 2 months ago, I believe. So our customer, like we have some introduction to our customer as well. So Zhongwei here, let me have my pointer ready. So Zhongwei here, they have been using our tool for almost 2 years. And it's in mass production now. And what I would like to say is, I overheard, I don't want to put the number there, but I overheard that their yield rate is pretty high. It's well above the average of the industry, probably 99 or something. Okay, another customer, Ryzen. So this is a panel that mentioned before. So they made the module of M12 half cell out of the cell made out of our tool. So what I want to mention is they made this half cell directly from the PECVD analyst. That proves that our carrier and our machine, our tool is suitable for half cell manufacturing. And here is Huasheng. They have also used our tool for half a year. So like 2 months ago, LONGi announced their new world record of efficiency. And this efficiency they have been achieved is down from our PECVD tool. It's our Microcrystalline HJT tool. They use our tool to set the record for 3 times in 6 months. That's really astonishing. And boosting the efficiency for the industry up to 26.3 for HJT. I would like to say this is not only a successful LONGi for us. I think, in my opinion, it might change the whole TOPCon HJT game a little bit, make it inclined to, that direction. So what we would like to call it a new era of microcrystalline HJT. And the efficiency of mass production is expected to exceed probably 25.5 with this new production line. So now, as Professor Wang just mentioned, microcrystalline becomes a very hot topic in the industry now. So I would like to make emphasis on the microcrystalline here. So it's proved that microcrystalline silicon from window layer improves the short circuit current and the fill factor. It will increase the efficiency for more than 1.5% or something. So what's the differences between microcrystalline or the amorphous? So what we see is the deposition steps are very similar, but the processing conditions, there are some differences. The differences involve like plasma frequency, like the power, like the dilution, like the pressure. And here I would like to emphasize on the plasma source side, which is plasma frequency and power. So it was mentioned in some of the paper that bombarding ion energy affects the nuclearization of the front window layer. And this is actually pretty straightforward as well, right? But what will affect the bombarding ion energy? I would like to talk about it. So here we have the bulk plasma here. So we know that in the chamber, in the PECVD chamber, what we do is we generate the plasma. And while there is a plasma, there is a sheath between the plasma and the chamber wall, right? And in the sheath, it dragged the ions down and accelerated. And eventually this ion will hit the wall. And how fast or how much energy the ion has, it depends on several things. One thing, straightforward, it depends on power. We can see the picture here. This is a ion energy, IED's ion energy distribution. So along different, for different power. So here it says different voltage, but different voltage means different power, right? So for 20 volt, 50 volt, 95 volt, you can see the energy of ion goes from 20 electron volt up to somewhere 50 and 90. So in order to make the microcrystalline silicon layer, I see some papers say you have to lower down the power. It might be okay in the lab. You can make it slower, make it lower power, but in high volume production, it's not acceptable. So we have to find a way that it will not slow down the depth rate. It will not slow down the throughput. However, it can make the microcrystalline as we wish. So this is a comparison between a powered electrode and the grounded electrode. So the left side is a powered electrode. You can see the ion energy for the powered electrode case. It goes somewhere between 80 electron volt to like 160 electron volt. Here the theta is like different time of a period you enter the sheath. It doesn't matter. So this is the range, 80 to 160. So in the grounded electrode case, it goes down to about 30. So a lot, right? So this is easy to understand. If you ground your electrode, your voltage will go down. Then someone will say, okay, my tool, we have my carrier grounded, period, right? But wait a second, it's not just that easy. It's not just that simple. So because there's no absolute grounding exists, there's always good grounding or bad grounding. So especially for RF or VHF, grounding is always a tricky thing. You can have your like two sides of your carrier grounded. You think it's okay, but actually it's not. And with that size, you grounded one point, and that means that point is grounded, not the whole carrier. So this raises another very tricky question for equipment designer and maker. How do you want to design your grounding system? So on this page, we show the frequency effect. So maybe a little bit, you see it? So this three we can see from 1 megahertz frequency goes down to 2 megahertz, goes up to 2 megahertz and 5 megahertz. You can see the ion energy here. The average ion energy goes down and down. So when the frequency goes up, the ion energy goes down. So that's a very clear law here. So on the other side, you can also see another evidence of crystalline volume fraction changes according to frequency. When it goes from 13.56 up to 95, the XC goes up and then down. So it looks like that 81 megahertz gives the best crystalline volume fraction. In this case, well, it just depends on, it's case by case, right? Not a general rule, but it gives us a ballpark of where we should be in. So this is a test on our tool. So we have this two tests here. The blue line is the input power level. It's always set to 600 watt. And then we have frequency 13.56 or frequency 40.68. You can see very clear the red line is the self-bias when we run it under 40.568. So the voltage is somewhere -3 volt. While in the case of 13.56, it goes up to like 14. So here you can see very clear that 40.568 has a better ion bombardment control than 13.56. That's why on our tool, we use 40.56 for the microcrystalline. So more advantages for VHF. Here, we can see as the frequency goes up from this point, it's 13, I believe, up to 40 and 60 and 80. This line is for electron density. In another word, plasma density, it goes up according to frequency for the same power level. So that means with the same power level, if you use 40, comparing to 13, you get higher depth rate, you get higher throughput. So this shows the depth rate according to frequency. We got the same result. So now we know that VHF is a better way to go if we want to make a microcrystal, but you might get into a dilemma of non-uniformity of VHF. It's not that easy. I think that's something Professor Wang wants to talk about, but he didn't have the time. Okay. Now, here is a chamber, a schematic of the chamber, showing you have this RF power here feed through and onto the electrode. You generate your plasma, but that's not all. You have also generated an electromagnetic wave going axial direction. In the chamber, it goes in from two sides. When these two waves meet and they interact with each other, and then we have the standing wave in the chamber. This right chart shows how the shape would be like for different frequencies. So for 13.56, it's okay, it's almost flat. You have, this is from chamber side, one side to the other side. You have the uniformity pretty good. But as the frequency goes up and up, you get a dome-shaped distribution. And also, if you go up more, you can get more complicated shape. But here, if we see it's 40.68 megahertz, you can see a dome here. But nobody wants a dome, right? You want it to be uniform across your carrier, across your chamber. So here is an experimental result for a standing wave effect. So they also use different frequency in the chamber. They measure the current, the ion current. So you can see it very clearly as frequency goes up, you get different shapes, and it's highly non-uniform for high frequency. So if you run a simulation of E-field, you can get this chart here. So here you have frequency from 13.56 go up to 40 to 100 and etc. And you have your non-uniformity in percentage. So epsilon here is a dielectric constant for plasma. So in our case, in the chamber, the dielectric constant is somewhere here between 6 and 10, something like that. That means you have non-uniformity of about 30% here for E-field. And if you calculate it into the power dissipation non-uniformity, you will get it like on the top, it's 1. And on the bottom, you can see it's almost 0.1. It's a 90% of non-uniformity for 40.68 megahertz VHF system. So that means even if you want to use it, you have to resolve this problem. Otherwise, it's not a production tool, right? So now in
Liang, could you please wrap up in the next 2 minutes?
Okay, last slide.
Okay, great.
Okay, so now in IE Sunflower, we are honored to say that we have already finished our design, our product. Our customer already use our VHF. Actually, the highest efficiency record, 26.3, was carried out in that chamber of VHF. And this shows some test result in our lab for VHF. This is the uniformity on our carrier. We have our carrier A by A here, and we have 9-point uniformity. It gets to the level of 4% of non-uniformity. This is thickness. And then also we have refractive index mapping here. the non-uniformity is about 2.5 something. And also you can see the crystalline volume fraction. Here is a Raman spectrum. So here it shows the crystal volume fraction. So on our tool, you can tune it up to 70%. It doesn't mean that the higher the better. You can, your process guy might get it down to somewhere you like 50, like 60, whatever. But this just shows we have the capability of have it up to 70%. And also this is a picture to show the film quality under SEM. You can see there's no holes, no defect. It's a high quality layer. So that's the whole report I have today. Thank you.
Okay, thank you very much for this very nice insights about microcrystalline silicon deposition. And yeah, it's really nice to see heterojunction efficiencies are going up. So since we are pressing with the time, I would be really happy if you can stay online and answer if there are any questions in the chat window.
Okay, sure.